Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
And dear students, the topic for today's class is generation of three-phase voltage. So with this we are starting the third unit, which is three-phase circuit. So let us first understand what is the meaning of three-phase signal or three-phase voltage, and we shall discuss how is it generated. Fine. So three-phase is a new term for all of us, isn't it? We have actually discussed single phase voltage till now, but we did not mention single phase there because if whenever you say AC signal, it is assumed to be a single phase signal. So we don't specify it. Okay. So single phase voltage is generated by using one armature winding. What does that mean? See, this is how the single phase signal is generated. Fine. Okay. So here we have the armature. Sorry. Now here we have armature and we have one set of coil, one armature. Okay. And it rotates in anti-clockwise direction with constant angular velocity. Fine. Now this rotates with constant angular velocity omega. And when it cuts the magnetic flux produced by the magnets, whether it is a permanent magnet or an electromagnet, it does not make any difference. When this coil or winding cuts the magnetic flux, alternating signal is generated. Now we have only one set of armature coil and hence one AC signal is generated, which is shown in the diagram. Okay, this is how the signal is generated. Now, if you have more than two armatures, two or more than two armatures, then how many signals will be generated? If you have two, then two signals will be generated. If you have three signals will be generated. So, a generator where we employ two or more windings, then the type of generator is called polyphase generator. Now what is the meaning of poly? Poly is multi and phase means winding or branches. Okay. So single phase means it has single winding. Two phase means it will have two windings and so on. Understood? Now this signal, if I assume this signal to be say V, small v represents instantaneous value. So this V will be given by assuming the signal to be sinusoidal signal, it will be Vm sin omega t. Fine. So let us see the next type of signal. This is a two-phase signal. So see, here we have two armature windings. One is A, another is B. Now one point here is very important, that these windings are displaced by equal electrical angle. Now what is the meaning? Now if you see the placement of A winding, it is something like this, and the placement of B winding is something like this, isn't it? So what is the phase angle? This phase angle is 90 degree. Correct? Both the windings are mutually perpendicular to each other. Now the signals generated by this type of generator will have the phase shift which is equal to the electrical displacement between these windings. What is the meaning? Now suppose winding A and B are arranged such that they have the displacement of 90 degree. Correct? These two windings are mutually perpendicular, so they have the displacement of 90 degree. So here both these signals will have the phase shift of 90 degree. Understood? Yes. So now here we have two signals. Okay, signal A and signal B. So how will I represent signal A? Signal A will be represented as, now A is the main signal, right? It will start at 0. So this is represented as Vm sin omega t, and signal B. Signal B is generated because of this winding, and this winding is placed 90 degree with respect to winding A, and you can see that here there is a phase shift of 90 degree. So this signal B will be represented as, now what is going to be the phase shift? Phase shift is going to be 90 degrees. Okay, so this is how two-phase signal looks like. Fine, is it clear? Yes. Let us see. Yes. Let us see how my three-phase signal will look like. So here we have three windings. Okay. I shall name them as A, B, C. Fine. Okay. So A is the basic signal. Now see how these windings are arranged. So this is A, correct? Now this is B, okay, and this is C. Now the electrical displacement or the angle between, this was B and this was C, right? So angle between A and B, this is angle, okay, is 120 degrees. So they are arranged such that they have angle 120 degree, and the angle between B and C is again 120 degree. So what will be the angle between A and C? It will be 240 degrees. Understood? Okay. So here now we have three windings. So three signals will be produced, right? So you can see that A is starting at 0, right? See, this is A winding. Now then you have B. Let me draw it once again. Okay. Now if this, let us use the color code so that it becomes very clear. Now this is A. Now here we have 180 degree, right? And here we have 2 pi, because we should be knowing here 90. So here will be 120, correct? Similarly, this is 360, right? So here we will have 240. 240 will be somewhere here, because middle, this point is 270, right? So this will be, this point is 240, because we want, very important points for us is 140 and 240 points. Fine. So the next signal, which is represented by B or red color, it starts at 120 degrees. Okay, got it? So this is how it goes. Now the third signal, which is represented by blue, it starts at 240 degrees. So this is how this signal looks like. Now of course you can extend it, right? So this is how my three-phase signal will look like. Got it? So you have to mark 3.0, 120 degree and 240 degrees. And corresponding signal will start at those points. Understood? Fine? Yes. So how are we going to represent the signal now? Now VA signal is the basic signal, the first signal, so it will be represented by Vm sin omega t. Now the next signal, okay, let us use the same color. Now this will be having 180 degree phase shift, so it will be represented as sin omega t minus 180, because it is lagging, it is coming after signal A, so it has minus. Similarly, VC will be represented as Vm sin omega t minus 240 degrees. Got it? So this was all about three-phase signal. Now how they are generated? So we have already discussed this, that we have a stator. Okay, in between you have a rotor. Okay, and the magnetic field is shown such that the north pole is downwards and south pole is uh, at the upper side. Then we have three coils. Okay, A, B and C, but the typical nomenclature for three-phase signal is R, Y and B. Okay, the nomenclature for this is R, Y and B. This A is actually R. Okay, then 120 degrees, so 120 is this one, B, so this is Y, and 240 degrees C, so this is represented by B. Okay, and then first R starts rotating. After 120 degrees, Y will start rotating. After again 120 degrees, B starts rotating. So the signal R leads. Then after 120 degrees, Y comes. After 240 degrees from R, or after 120 degrees from Y, B comes. Got it? So this is how the signals are generated. Fine. So let us derive the equation now. Yes. So as I have said, that A represents R coil, B represents Y coil and C represents B coil. These are the standard names for those coils. Okay. So basically this is how the signals were represented. We have already seen that why the signals are represented like this, isn't it? R signal is the first signal in the sequence, so it does not have any phase shift. In fact, it is the reference point. Then comes Y, which is 120 degree behind VR, or it lags VR by 120 degree. Then comes VB. Now remember, minus 240 shows the phase shift with respect to R and not the phase shift with respect to Y. Fine? Okay. Now what is going to be the total resultant? Total resultant signal will be the sum of all these individual voltages. So we will add VR, VY and VB. So the resultant signal will be VR plus VY plus VB. So we will, we will put all the values and let this be equation number 1. So we have written it as resultant equal to Vm sin omega t plus Vm sin omega t minus 120 degrees plus Vm sin omega t minus 240 degrees. Now what we are going to do is, in order to simplify it, we will consider this minus 180 as minus 120 plus 60. And similarly, we will consider 240 as minus 180 minus 60. So these two values are going to give me the same value, isn't it? Minus 120 and minus 240. Now why are we doing this? Because I have to convert this equation, okay? I have to actually simplify this equation. So this becomes A, B. So I have sine A plus B, and this will be again A, and this is B, so minus B. So I will have sine A plus B and sine A minus B. And I know how to minimize such kind of equations. Okay? Yes? So the next equation is written like this. So equation 1 can be rewritten as this. This becomes equation number 2. Now, as I said, we have converted this equation as sine A plus B and sine A minus B. Please ignore this here. This is sine. Yes, so this is sine A minus B. Fine? Okay. So what is sine A plus B plus sine A minus B? It is 2 sine A cos B. It is 2 sine A cos B. So my equation 2 will become Vn sin omega t Okay, 2 sin A cos B. What was A? What was A here? Come on. It was omega t minus 180. Okay, and here what was B? 60 degrees. Fine. So this becomes 2 sin A cos B. Okay, so we have reduced the equation. Now we will put the value of cos 60. Yes. Okay. Before that, we will replace this as this one. Okay, we will take this minus sign outside and sin pi plus theta becomes sin pi minus theta becomes this. Fine. Sorry. So when we simplify this, we get minus 2 cos omega t. Okay. Yes. So here we have sin theta minus pi. So that is minus sin theta. So this was the simplification we used here. Fine. And then we will put the values. So cos 60 is half. That is 1 by 2. Now what will happen now? This 2 and this 2 will get cancelled. And what do we get? We get Vm outside bracket because Vm was common. Sin omega t, 2 and 2 got cancelled. So here again we have sin omega t. So again these two will get cancelled. So what is the answer? Answer is 0. It means what? The resultant voltage is 0. Right? The resultant is 0. So sum of 3 voltages at every instant is 0. This is very important point here. That in 3-phase voltage, the sum of 3 voltages at every instance is 0. Fine, let us discuss the advantages of 3-phase voltages. Now 3-phase power generation and distribution is advantageous over single-phase power distribution because of several reasons. Because it requires, the 3-phase distribution requires lesser amount of the wire, it means copper and aluminium, for transferring the same power which was compared to single phase. It means suppose if you want to transfer say 100 watts of power, so you will require more copper or aluminium if you want to transfer single phase supply, and you will require lesser amount of copper or aluminium to distribute same 100-watt power. So that is cost effective, isn't it? Now the size of the 3-phase motor is smaller. So for, now we know that miniaturization is a very important point in our day-to-day life. We want everything to be thin, small, correct? Earlier we were using big TVs, now they have become very thin. Similarly, mobile phones. So if the size of the motor becomes small, then we would prefer it, isn't it? The next point is they are self-starting. Now, what is self-starting? It means you do not require, you do not require any external help to start that motor. You are going to see this phenomenon when we will go to the 5th and 6th unit. Don't worry about it. You can just keep this thing in your mind that few motors require external help. Okay? And then they have better power factor regulation, and 3-phase generators are smaller in size. Okay? Those were the advantages because of which 3-phase signals are preferred. Now we shall discuss few important terms. Now what are those few important terms? Now we are going to use these terms frequently in this unit. So first term is phase sequence. What is the meaning of phase sequence? Now it is the sequence in which the voltage in three-phase system reach their maximum possible value. It means the sequence in which your signal starts or reaches the maximum value. Now when we started this class, after say 5 minutes, we discussed that first R starts and then Y and then B starts. So what is the sequence? R, Y and B. Okay. The second is phase current. The phase current is basically a term to represent the current flowing through each winding. So we have winding R. We have winding R, correct? So we have phase current as IR. Then we have winding Y and similarly winding B. So these are all called phase currents. Then we have phase voltage. It means what is the voltage induced in each winding. Each winding, okay? Now comes line voltage. Now you must be thinking phase voltage, okay, voltage induced in each winding. What is a big deal in it? Yes. Now here we have two terms. In single phase we do not have such different terms. But in three phase we have another term called line voltage. Now what is line voltage? It is the voltage between two terminals. Now what is the meaning? Now suppose this is R. Okay, this is say Y and this is B. Okay, so I have taken this. Suppose this is a star connection. Okay, so VR, this is IR, correct? So some voltage will be there, VR. But suppose I am taking this becomes, if I am only representing it by R, this becomes phase voltage. Okay, but suppose I am measuring the voltage between R and Y. It means between R and Y. Then this becomes line voltage. Got it? Similarly, this voltage, say Y and B, then this becomes line voltage. Otherwise, VY only phase voltage, VB only phase voltage. But between R and Y, between Y and B, or between B and R, correct? So suppose here I measure the voltage VBR. Then this becomes line voltage. And remember, we have to move in this direction only. R to Y, Y to B and B to R. Understood? So this was line voltage. Similarly, we will have line current also. We shall erase this. We will go to the next term. Line current. So we have line voltage, line current. So it is a current flowing through each line. Okay, line voltage is there. So whatever current flows through that line voltage is the line current. Then we have balanced system. So a system is called, any three-phase system will be a balanced system if it satisfies these three conditions. Now what is these three conditions? This is very important point, and let me share with you that in our syllabus in BEE only balanced systems are there. We are not supposed to discuss unbalanced system. Okay. So a system is balanced when the magnitude of the voltages in three phases are equal and they have phase difference of 120 degrees. So please remember that here the magnitude of the voltages in three phases will be same and they will have the same phase difference of 120 degrees. We cannot change it. It has to be 120 degree and the magnitude has to be same. Similarly, the magnitude of the current will also be same and they will also have a phase difference of 120 degrees. Okay, and the third condition is the loads across these three phases are identical. It means whatever load you are connecting, it has to be same across three phases. It means what? I'll just give you an example. Now again we shall draw R, Y and B. Okay. Now suppose I am connecting an impedance Z. Now if it is resistive, then I have to connect resistive load at R and at B also. The same load has to be connected. If it is inductive, if I am connecting inductive load at R, I have to connect inductive load at Y and B. If it is capacitive, same. If it is combination of resistor and inductor at R, then the same has to be connected across Y and B. You cannot connect R at, resistance at R, inductor at Y and capacitor at B. Got it? I hope this point is clear. So the impedance should also be the same. It means the load. Okay, the load has to be same. Then comes the symmetrical system. Now symmetrical system is a system where these three voltages have the same magnitude, same frequency, but the phase difference is 120 degrees. Okay. So at the end we shall discuss that what we learnt today. So today we learnt that how three-phase voltage is generated, and we also learnt that three-phase voltages are equal. We are talking about the balance system. Fine. These voltages are equal in magnitude and frequency, but they have phase shift of 120 degrees. Then we also learnt that the sum of these voltages is 0. And secondly, we also saw that three-phase signal is advantageous over single-phase signal. So by this, we come to the end of today's lecture. We shall meet in the next lecture. Thank you.